the concept of finite differences is important for interpolation of a tabulated function. We introduce forward difference operator as follows. So, given a set of values xi, yi of a function y is equal to f of x, where xi's are equally spaced and xi is x naught plus IH, I is equal to 0, 1, 2, 3 up to n. The forward difference operator delta is defined as follows. So, delta on yi is yi plus 1 minus yi for I is equal to 0, 1, 2, 3 up to n minus 1. So, when I is say 0, delta on y naught will be y1 minus y naught. Delta on y1 is y2 minus y1 and so on. Delta on yn minus 1 will be yn minus yn minus 1. So, what does delta do? When delta operates on y naught, it is equal to the value that y takes at the next point, namely y1, which is y at x1, namely f of x1, minus y naught, which is f of x naught. So, here by yi I mean f at xi for I is equal to 0, 1, 2, 3 up to n minus 1. So, these are the first order forward differences. The higher order forward differences can be similarly obtained. Say if I want the second order forward differences, then I would like to get what is del square on yi. So, this will be delta on delta yi, that is delta on, we know delta yi is yi plus 1 minus yi. So, this will be delta on yi plus 1 minus delta on yi. So, these are first order forward differences. So, I use the definition and write delta yi plus 1 as delta yi plus 2 minus yi plus 1 minus yi plus 1 minus yi. So, that will give me yi plus 2 minus twice yi plus 1 plus yi. So, I can compute the second order forward differences using this definition for values of I starting from 0, 1, 2, 3 etc. up to say n minus 2. And we can follow this definition and compute higher order differences using this definition. So, now that we know how to obtain the forward differences given a set of say n plus 1 values xi, yi for equally spaced points, we present the forward difference table here. Why is it needed? With the help of this table, when we form this table, we will be using this table in writing down an interpolation polynomial of degree at most n when we are given a set of n plus 1 points. It is easier to write down the interpolation polynomial for a set of given discrete values. So, we would like to see how we can form a forward difference table. So, let us be given the values of x and the corresponding values of y at a set of points say x minus 2, x minus 1, x naught, x1, x2. So, the corresponding values of y are denoted by y minus 2, y minus 1, y naught, y1, y2. So, we form the various order forward differences. So, let us compute delta y, the first order forward difference. So, delta y minus 2 will be y minus 1 minus y minus 2. So, the value at the next point minus the value at this point. So, delta on y minus 2 is y minus 1 minus y minus 2. What is delta on y minus 1? It is the next value y naught minus y minus 1. Delta on y naught will be y1 minus y naught. Delta on y1 is y2 minus y1. So, these are the first order forward differences. Let us compute the second order forward differences. So, they are denoted by del square of y minus 2 and that is equal to, it is going to be now delta on y minus 1 minus delta on y minus 2. Then del square on y minus 1 is delta on y naught minus delta on y minus 1. Then del square on y naught will be delta y1 minus delta y naught. So, these are the second order forward differences. Let us go to the third order differences, del cubed y. So, we have del cubed on y minus 2 will be del square on y minus 1 minus del square on y minus 2. Then del cubed on y minus 1 will be del square on y naught minus del square on y minus 1. So, let us now move on to compute the fourth order forward difference, del power 4 on y. So, that will be del power 4 on y minus 2 and that is equal to del cubed y minus 1 minus del cubed y minus 2. So, we observe that we are given a set of 5 points and the corresponding values at these points in this table. So, we know that there exists a polynomial, an interpolation polynomial of degree at most 4 that interpolates the function f of x at the set of these 5 points xi, yi. And we observe that we have computed the various order forward differences of this polynomial namely the fourth degree polynomial that interpolates the function at a set of 5 points. We will show that when we take forward differences of this polynomial of degree 4, which I call as P4 of x, the fourth order difference of P4 of x will be constant, and the fifth and the higher order differences will all be equal to 0. So, the kth order difference of P4 of x will be 0 for k greater than or equal to 5. I will just repeat again. We have a set of 5 discrete points at which the function values are given. So, there exists an interpolation polynomial of degree 4, P4 of x, that interpolates this function at a set of these discrete points. We will show later that the fourth order difference of a polynomial of degree 4 is constant, and higher order forward differences of this polynomial of degree 4 will be 0. This result will be used when we find out the interpolation polynomial that interpolates this function at a set of discrete points. And you also observe from this table that you have fourth order difference of y computed, and this is constant, and the higher order differences will all be 0. Y minus 2 is called a leading term. And you also observe that along this diagonal, the suffixes for y minus 2, delta y minus 2, del square y minus 2, del cubed y minus 2, del power 4 y minus 2. So, the suffixes are all the same. And when you compute, say, a first order difference of y, you write that entry between any two elements in the previous column. That is how you have formed this forward difference table. For example, how did you write del square y minus 2? You placed it in the column for second order differences, and this is located in between the two entries which you used to compute del square y minus 2 in the previous column. What are those entries? They are delta y minus 1 and delta y minus 2. So, you place the second order difference del square y minus 2 between the two entries which appear in the previous column. So, this is how a forward difference table is formed for a set of values of a function which is given in the form of a table of values. So, as we said, we would like to make use of this forward difference table and find an interpolation polynomial for a set of given discrete points. At this stage, I would like to introduce another operator, which is called the shift operator. The shift operator is denoted by E, and it has the following property. So, let y be equal to f of x, and let x take values x, x plus h, x plus 2h, and so on, x plus nh, and let the corresponding values of y be f of x plus h, f of x plus 2h, and so on, f of x plus nh. So, what is the property of E? E on f of x is f of x plus h. And what is E square on f of x? It is E on E of f of x, but E on f of x is f of x plus h. And what is the property of E? E on f of x plus h is f of x plus 2h. So, you observe that E square on f of x is f of x plus 2h. So, now you should be able to tell me what is E cubed on f of x. It is going to be f of x plus 3h, and so on. So, we can write what is e to the n on f of x. That is going to be f of x plus nh. Suppose say I take these values as x naught, x1, x2, etc., xn with xi as x naught plus ih for I is equal to 0, 1, 2, 3 up to n. Then I know that E on f of x naught. But what is f of x naught? It is y naught. What is E on f of x naught? E has the property that it produces the value f of x plus h when it acts on f of x. So, here E acts on f of x naught, and therefore, it gives you the value y1. What is y1? It is f of x1. So, what is E square on y naught? It is E on E of y naught, which is E on y1. So, that produces y2. So, E square on y naught is y2. So, continuing this, we have E to the n on y naught will be equal to yn. And let us see what is E minus 1 on f of x. It is going to be f of x minus h. That is, x minus 1 is a point which is x naught minus h. X minus 2 is a notation for the point x naught minus 2h. So, e to the minus 1 on f of x will give you the value of the function at a point which is previous to x, namely it is x minus h. So, that is what we have denoted by x minus 1. What is e to the minus 2 on f of x? It is going to be f of x minus 2h. So, we will use the shift operator and the forward difference operator and see whether we can connect the two operators. Let us start with E on y naught, and that is equal to y1. What about delta on y naught? Delta on y naught is y1 minus y naught. But I know I can write y1 as E on y naught. So, delta on y naught is E y naught minus y naught. So, it is E minus 1 on y naught. So, the role of delta on y naught is identically the same as the role of the operator E minus 1 on y naught. So, delta is related to E minus 1 by delta is equal to E minus 1 or E is 1 plus delta. So, the shift operator and the forward difference operator are related by E is equal to 1 plus delta. So, our goal now is to make use of the forward difference table and the property of the shift operator and the relation between the shift operator and the forward difference operator in writing down an interpolation polynomial that interpolates a given function at a set of discrete points which are equally spaced. We now derive Newton-Gregory's forward interpolation polynomial that interpolates a function which is given in the form of a table of values. So, our derivation is for a set of equally spaced points at which the function values are specified in the form of a table. So, let y is equal to f of x be a function whose values are given at x, x plus h, x plus 2h, etc., x plus nh. The corresponding values of the function are f of x plus h, etc., f of x plus nh. So, we have a table of values of the function at a set of points x plus h, etc., x plus nh, and the corresponding values of this function, namely f of x plus h, f of x plus 2h, and so on, f of x plus nh. What is our problem? Given a set of n plus 1 points, we would like to obtain a polynomial of degree at most n that interpolates at a set of points x f of x, x plus h f of x plus h, etc., x plus nh f of x plus nh. So, we want to construct this polynomial of degree at most n that interpolates the set of n plus 1 points which are given to us. Suppose say we are able to do that, and we would like to now estimate the value of the function at some point x plus ph, where p is a real number and x plus ph is such that it lies between x and x plus nh. That is our problem. Problem 1 is to obtain an interpolation polynomial that interpolates the function at a set of given points. When we are done with that, what is the estimate of the function f at x plus ph, where p is a real number and x plus ph lies between x and x plus nh. So, I can write down f of x plus ph as e to the power of p on f of x. That is the property of the shift operator which we have seen. E to the p on f of x gives you f of x plus ph. But we know that e power p is 1 plus delta to the power of p on f of x, because e and forward difference operator are related by e is equal to 1 plus delta. So, at this stage I can expand 1 plus delta power p using binomial theorem. So, it is 1 plus p into delta plus p into p minus 1 by factorial 2 into del square plus etc. P into p minus 1 into p minus 2 into p minus 3 etc. p minus n minus 1 by factorial n into, when I have p into p minus 1 by factorial 2, I have del square. When I have p, p minus 1, p minus 2, p minus 3 etc., p minus n minus 1, then it is del to the power of n plus etc. operating on f of x. So, the question is, how many terms will appear in this expansion? We have already seen from our forward difference table which we formed for a set of 5 values, we can fit a polynomial of degree 4 and the 4th order forward difference is constant and higher order differences are 0. So, we shall now prove that result in general, namely given a set of n plus 1 points, one can fit a polynomial of degree at most n, namely Pn of x, and the nth order forward difference is constant and higher order forward differences beyond n plus 1 are all 0. We will make use of that result so that the terms here will be such that they will terminate here, because the nth order difference is constant and the higher order difference will be 0. So, the terms will just be those which appear within the brackets operating on f of x. So, before continuing this step and finding what the polynomial is, we shall prove the result that given a set of n plus 1 points where the xi's are equally spaced, the nth order forward difference of a polynomial of degree n is constant and n plus 1th and higher order differences are 0.